Okay, so this is going to be redundant. I'm doing this now for the people that showed up a little bit late and also for the recording. Our quiz is Thursday. It's on chapter 9, no notes. Last night, I covered in a lot of detail the complex numbers and solving equations using either the quadratic formula or something called the square root property. Okay. Tonight, I want to talk about equations that are reducible to quadratic. And the review from last night tonight served as a great review for Thursday's quiz and also the chapter 9 part of exam number 3. So here we go. First thing I'm going to do is make it equal 0. So to do that, I'm going to move the 3 and the 9 over here. So we have 2x to the 2/3 minus 3x minus 9 equals 0. Remember, the shortcut, if you haven't figured it out, is when you move something from one side to the other, technically you'd like take 9 away from both sides. But the lazy way of thinking that is when you move it over, it changes its sign. It changes from positive to negative or negative to positive. But that's an aside. Oops, this is x to the 1/3. Now, what we did is we made up a variable. We said let u, and you can use any letter you want, equal x to the 1/3, the lowest power, x to the 1/3, okay? And that implies if you squared both sides, that also means that u squared is going to be x to the 2/3. So if you do just this, u is x to the 1/3, then by squaring both sides of this, you get u squared as this. So what that means is this equation is now 2u squared minus 3u minus 9 equals 0. And that's an equation you can solve either by the quad formula or by factoring. Okay. Turns out it will factor, oops, equals 0, dummy. So this is 2x and x and a minus 3 and a plus 3. It's like that. Okay. Again, your ability to factor, and I was a little bit dismayed at some people on the exam number 2 still couldn't factor. It's killing you guys. Okay. Factoring is critical. All right. Split this up. We get 2x plus 3 equals 0. Or x minus 3 equals 0. Here, I'm going to jump to the answer. If you subtract 3 and divide by 2, you get, whoops, I'm wrong. Check your notes, guys. My variable is u, 2u, u. Bad way to start the night, u. I get u equals negative 3/2 or u equals 3. It's important to keep your original variables separated from your new variable, your substitution variable. I screwed up there. Excuse me. So we solved for u, but the original problem was x. So we unsubstitute, and right here it says u is the same as x to the 1/3. So we can say x to the 1/3 equals negative 3/2, or x to the 1/3 equals 3. And usually that bugs a whole lot of people. The unsubstituting, the going back from u to the original variable, whatever it was. Now, the thinking part here is, okay, well, fine. How do I get rid of x? How do I get x rather all by itself? How do I get rid of the 1/3 power? There's 2 ways of thinking of that. First way, okay, and you can choose either way. It doesn't matter to me. The 1/3 power is the same as the cube root. Okay, 1/3 power is the same as the cube root. So how do you get rid of a cube root? With a cube power. And that gives us x equals, this will be negative 27 over 8. That's one way of doing it. It's recognize that the 1/3 power is the same as the cube root. And so transfer it into a root of some form and then cube power it. The other way, if you're a little bit tricky, is to raise it to a power, okay, the 3rd power, because it's the reciprocal. And when we do a power raised to a power, we multiply them together. So that becomes x to the 3 over 3, which becomes x to the 1st, which is just plain old x equals the 27. So our solution set for this particular problem is 27/8 and 27. And that is a pretty standard problem that we like, that you'll see on a lot of exams where we use substitutions. Okay, you get rid of the ugliness by substituting for the ugly part of it, the x to the 1/3 and the x to 2/3. Okay, solve a prettier problem and get the u answers, but then unsubstitute back to the original variable, and then solve those little ones. Okay, questions on that? You're sure? Okay, the key at the start was to make it equal 0 and let your new variable, again, why all the books in the world use u, I don't know, but they do. Okay, but they let it equal the lowest weird thing, x to the 1/3 or whatever that is, the smallest power of weird x, not the big one, the small one. Okay, all right, want to erase and give you a problem I think is similar to this. It's going to use the substitution, but it's going to be totally unlike this. But your hint is you're going to substitute. You're going to get rid of the ugly part of the problem and put something prettier in its place for a little bit. All right, can I erase this? Okay, don't hear nobody yelling. Right. Don't panic. 2x plus 1 quantity cubed plus 2x plus 1 quantity squared minus 6 times 2x plus 1 equals 0. You have two ways of doing this problem. I'm going to be quiet and let you think about it a minute. Okay. You have two ways. One is you could cube this thing out, square this thing out, multiply by -6, combine like terms, and then go from there. Probably factor a quad formula or something. I don't know what. And when you cube this out, by the way, you have to do 2x plus 1 times 2x plus 1 times 2x plus 1. Okay. And that's insane. It's pretty darn ugly. So I would suggest that's not the way you want to do it. What you want to do is use a substitution. I'll let you get started. What if you said, let u equal 2x plus 1? Go from there, see if that helps you a little bit. We'll pause. Okay, I forgot to turn on the recording. So those of you who are watching this video, you're SOL. One way of testing whether you know somebody is a function or not is if I give you a list of ordered pairs and you ask, does each X go to a single Y value? Okay, yes, 3 goes to one answer, or 7 goes to one answer. Okay, so yes, this is a function. The domain just means list all the X values. The range just means list all the Y values. Okay, and there's another one I erased here. Then we went to this problem, an ellipse, and I give you some information, but is it a function? And the answer is no, it is not a function. For a couple of reasons. If you have a picture, then you can do what's called the vertical line test. If your vertical line hits more than one point on the graph at a time, okay, but you got to have the picture there, okay? But if your vertical line hits more than one point at a time, it is guaranteed not to be a function. Now, the question is why? Okay, because let's say you do a vertical line right there, then this becomes the X. If you read down to the graph over here, you have a Y value. Okay, right here's a Y value. But if you read up to the graph and over here, you have another Y value. So this X matches with two different Y values. Okay, we have an X, whatever it is, going to the Y on top and also going to the other Y on bottom. Okay, and that says, no, 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 X can only go to one answer, and we have it going to two different answers. So it's not a function. And your vertical line test is just an easy, lazy way of showing that. Okay, so to determine if somebody is a function or not, you pass the vertical line test over it. That's not a function. Now, the domain and range on this is tricky, and we had trouble with this earlier in the semester. Notice, these were called discrete points, individual points, 3, 1, 7, 1, 11, 1. But this graph is made up of an infinite number of points. Okay, you couldn't possibly tell me all of the X's. Like here, I could tell you what the X's were. But because there's an infinite number of points, you can't tell me all of them. So you had to have some math notation for the domain. So for this one, the domain is everything from -8 up to 7. All of the X's from -8 up to 7 were being used. So that's the domain. The range on this one, okay, is the Y values. Well, all of the Y's from -2 up to 6 are being used. They're all up and down here. All these are Y values up and down here, -2 to 6. So no, it's not a function, but we can still determine its domain and range. This one, we had to use interval notation to talk about domain and range because there's an infinite number of X's and an infinite number of Y's. So we had to use a special notation that allows us to talk about the infinite values. All right, that's it that I want to talk about for what is a function and what are some of the ways I'm going to ask you, or mom is going to ask you. So I need to erase the board, move on to a new review topic. Is that okay with everybody? That should be like a review of what we talked about last night. and a little bit more. We added a little bit more tonight. Questions? Okay. Then while we're on the topic of functions, we introduced a new topic related to functions called composition. Functions, composition of functions. And that's where we introduced a little tiny circle. Now you're supposed to, okay, and so we write F circle G. You're supposed to say F composed with G, but most people just say F circle G because they're lazy, or G circle H, or whatever the functions are. Okay, whatever, it doesn't matter. We get lazy. You're supposed to say G composed with H, or F composed with G, but everybody's lazy. But that's called function composition. Well, how does it work? It puts one function inside of another function. Function inside, whoops, other function. So let's take an example. Let's make up a nice f of x, I don't know, 3x minus 6. And I'm just making these up. G of x is 5x plus 1. Okay. So the first thing we can do is I can do real simple arithmetic. What is f of g of negative 2? So take a second and work on f of g of negative 2. Remember, we say it from the outside in, but we actually do it from the inside out. Okay. I think I get 21. Let's see. First thing we do is we stick negative 2 into the g function. So that's 5 times negative 2 plus 1. 5 times negative 2 is negative 10 plus 1 is negative 9. Oh, I was wrong. 33 negative. So what that means is we've just turned this problem into f of negative 9. Okay, g of negative 2 is worth negative 9. So we replace g of negative 2 with negative 9. That's what it's worth. But now we have to do a whole nother problem. What's f of negative 9? And all that means is plug negative 9 into the f function. Okay, and so how do I do that? The f function says 3 times negative 9 minus 6. It's negative 27 minus 6. That's 33 negative. And that's simply your answer. Again, you're not solving anything. You're just doing arithmetic. You're plugging numbers in, doing arithmetic. So you just circle your answer. And that's about the easiest way I can ask a function composition. A function inside of a function is giving it to you this way. Okay, but mathematicians are out to get you. They say things like find G circle F or G composed with F. No numbers, just that funny little circle thing. Okay, so first off, you have to remember that this actually is just math shorthand for this. G circle F is G of F of X. Okay. You have to know that those two are the same. Now, how do you do this when there's no numbers? Well, you start on the inside, just like over here. We took -2 and plugged it into G. We're going to take X and plug it into F. Well, that's what that says. If you take X and plug it into F, that's what you get. So this problem becomes G of 3x minus 6. Okay. Another way to look at it is f of x and 3x minus 6 are the same. That's what the equal sign means. F of x is the same as 3x minus 6. All right. Now, how do I plug that into the g function? What's the g function say? It says, whatever you give me, what am I going to do? I'm going to multiply it by 5 and then add 1. Whatever you give me, I'll multiply it by 5 and add 1. Well, I'm giving it that. So I'm going to, okay, 5 times 3x minus 6, add 1, because that's what the g function tells me to do. So that's 15x minus 30, add 1, because you distribute. So I get the final answer for G circle F is 15x minus 29. So G circle F became that. Okay, again, G circle F, you have to know it means G of F of X. Okay, so I replaced F of X with what it's worth. F of X is the same as 3x minus 6. And then I plug the 3x minus 6 into the G function. Okay, I'm going to do one more. I'll let you do one more. Any questions before we do one more? Okay, then I'll erase this. Let's do, that was number 2. I should have put that up there. Let's do problem number 3. Using the same f and g of x, I want you to find f composed with g, fog, f circle g. Take a second to find that one. So f circle g is the same as f of g of x. Okay, those are the same. G of x is the same as 5x plus 1, so this becomes f of 5x plus 1. Now, what's this say? This says go to the f function and input 5x plus 1 in place of x. Or so the other thing, it says, what does the f function say to do? It says, whatever you give me, I'm going to multiply it by 3 and then subtract 6. So I'm going to take this, multiply it by 3 and subtract 6, and then simplify it. So f circle g is this. Yes or no? That's it.
Can you put f of g equals 15x minus 3?
Sure. Sure. That might even be nicer, prettier. F circle g equals 15x minus 3. Because that kind of ties it all together. Yes. Anybody else? Okay. Then there's one more thing we covered last night that I want to review before we get off into brand new stuff. So I need to erase the board. Is anybody still copying or taking notes? Okay. So the last thing we covered last night, and I covered it really quickly, and I totally understand if you just kind of wrote it down and said, "Hey, I don't get nothing." We covered the idea of inverses. The object of an inverse is to undo a function or operation, undo it. And I started with examples. I said, well, let's say you start with X and you add 3 to it. What do we know is the undoes the 3? Subtracting. We've learned that adding and subtracting, okay, cancel each other out. So we call those inverse functions, or actually in this case, they're called inverse operations. We also learned last night that if you multiply X by 5 and then divide it by 5, you still get X. So we've learned that multiplication and division are called inverse operations. And then I think last night I also gave you, okay, the square root of the square power. And that also is X. Okay. Math wants everything we do to be undoable. In other words, if we change it into something like add 3, we want to be able to change it back to what it was originally. Okay. So if we take a function like 2x minus 5, okay, and I know that f of 7 is 2 times 7 minus 5, which is 14 to 5, which is 9. So the f function takes 7 and turns it into 9. I want to know mathematically what function will take 9 and turn it back into 7. What math rule will take 9 and turn it back to 7? I already know that this rule takes 7 and turns it into 9. But I want the inverse of this rule. I want to be able to go backwards. So I gave you some steps, which I'll put up on the board again. Now, you guys need to have access to these notes throughout this chapter, because we're learning inverses and we're learning them on pretty simple functions. By the end of this chapter, we're going to be finding the inverses of really complex functions, but the steps are going to be the same. First, we're going to replace f of x or g of x or whatever with y. Okay. Second, we're going to swap x with y. Third, we're going to solve for the new y. And fourth, we're going to replace the y with this notation, f to the negative 1 equals x of x. Now, we don't say f to the negative 1. This is f inverse of x. F inverse of x. Okay. So the -1 power on a function means different than the -1 power, whoops, on a variable. On a variable, it just means do the reciprocal. On a number, it means do the reciprocal. 1/3, sorry. Okay. But on a function, it means something totally different. The -1 power on a function means the inverse of it. So let me do this one, and then let me have you guys walk through a couple. So here is f of x. And we've seen that f of x takes 7, turns it into 9. I want to find the inverse of f of x. Find the inverse. So first thing I do is write it as y equals 2x minus 5, because that's the first step. Replace f of x with y. Second step was swap x's with y's. Just the y and the x, just switch places with them. Okay. Third, solve for y. In other words, get that y all by itself. So I would add 5. Then I would divide everybody by 2. Okay. And there's the glare. Okay. And then the last step is replace the y with f inverse. Okay. Now I'm also going to switch this around. So I write f inverse of x equals x plus 5 over 2. I just like my f of x. Oops, that wasn't very good. Let me rewrite it so it's not in the glare. Better. Okay. I just like my f of x on the left-hand side. If you wanted to put it over here, that's cool. I don't care. So that's how we found the inverse. That's how we found the inverse of x. I followed these steps. Okay. And again, as we get more and more complicated functions, we're going to follow the same steps, but they're going to be harder to do. And you're going to have to do some thinking and a lot of critical analysis in here. Okay. And just for fun, does this function, f inverse, take the 9 and turn it back into a 7? If I take f inverse of 9 here, the answer, that's going to be 9 plus 5 over 2. Plug it in there, 9 plus 5 over 2. That's going to be 14 over 2. That's going to be 7. So yeah, the inverse took 9 and turned it back into 7. It undid what f did. F changed 7 into 9. F inverse changed 9 back into 7. So these two functions are related to each other. They're the inverses of each other. That's why they have the same name, f, but this is the f -1, f inverse, shows me that they undo each other. All right, before I let you guys do a couple problems, I'll make them up in a minute. Questions about what I've done up here? Okay, then I'll make up some problems for you to do. Okay, so my instructions are going to be find the inverse of each. Okay, number one, we'll have f of x equals 2x plus 3 over 5. And number two, we'll have g of x equals the square root of x minus 5. Okay, so I have two different problems. I want you to find the inverse of f following these rules and the inverse of g following the same rules. Okay, so here we go with number one. Y equals 2x plus 3 divided by 5. Swap x and y, so x equals 2y plus 3 divided by 5. Somehow we're supposed to solve for y. Okay. Personally, I like to turn it into proportion by cheating a 1 underneath so I can cross multiply. Now, I want to take this opportunity. I've got most of the class with me here. People tried to cross multiply on exam 2, and I don't know what you're doing. When you take this and you cross multiply, you do 5 times x equals 1 times 2y plus 3. When you cross multiply, you have no more fraction. A lot of people did some cross multiplying and had some bizarre answer that was still a fraction. The reason for cross multiplying is to get it out of fraction form into a normal equation form. Okay, enough talk. You'll see your tests tomorrow night. I'll give them back to you. So anyways, this becomes 5x equals 2y plus 3. Now we're supposed to get y alone. Solve for the new y. Get y alone. So, okay, what am I going to do? Subtract 3. Divide by 2. Where's my glare? Okay. And change the y into f inverse of x. And that would be my inverse. It's still partially in the glare. Is that okay with everybody? Okay, I follow these rules. Swap x with y, then use my algebra skills to solve for the new y. Okay, I like to see this as a proportion. It's easier for me to cross multiply than I had to solve for y. And that's it, I'm done. Okay, now number two got a little bit trickier. Again, we write it as y equals the square root of x minus 5. Swap x with y, so x equals the square root of y minus 5. And now you've got to get y alone. Well, wait, I've got to get rid of a square root symbol. The only thing I know that gets rid of a square root symbol is to square both sides. So that gives me x squared equals y minus 5. Get y alone, so x squared plus 5 equals y, add 5 to both sides, and then rewrite this as g inverse of x equals x squared plus 5. I think that's empty. Okay or not okay for finding the inverse of a function?
Okay.
I'm eating the ink or papers first. Okay. Crap. I mean, darn it. So I kind of want to leave that. That'll get you through most of mom work in 10.1. We got a few things to talk about, but that's finding the inverse. Okay, no questions on my work because I want to add something to this now. I want to make it not more difficult, but I want to talk about more information related to this. Can I erase these? Okay, so one of my favorite questions, whether it's in mom or not, okay, I've forgotten already, but one of my favorite questions is to give you the picture of a graph, okay, something like, oh, I don't know, let's take, no, that wouldn't be right. Okay, and let's say this is -5, -1. And let's say this is -3, 2, and this is 4, 2, and this is 6, 7. Okay, so kind of sketch that out for a second. This is a partial graph of some function. Again, we'll give you the picture. I don't know what the rule was. I have no idea what the rule was. Okay. I want you to sketch its inverse. Sketch its inverse. Okay. And the key is right here. Okay. In all inverses, whether we do it with math rules, functions, and stuff like that, or whether we do a sketch, the X and the Y will always be swapped. Always. Okay. What's that mean? Well, this is the point -5, -1. If we swap the X's and the Y's, it will become -1, -5. Now think about this. This connects to -3, 2. But if we swap the X's and the Y's, it'll go to 2, -3. Something like that. Boom. But back up here on the black graph, -3, -2 goes to 4, 2. But if we swap it, that'll be 2, 4. Something like this. And 4, 2 matched with 6, 7. So if we swap it to 7, 6, this should go out here to something like that. Well, that's not quite right. It should look something like that. And that would be 7, 6. So what did I do? In order to sketch the inverse of a picture of a graph, all I did was swap the ordered pairs, swap the X and the Y. 5, -1 became -1, 5. and I plotted the point. -3, 2 became 2, -3, and I plotted the point. So all I did was find the inverse of each key point and then connect the dots. That's all I did. That was it. Okay. That is a favorite question of mine. I put that on every single exam for chapter 10. Okay, that's been on every, I'll give you the picture of some graph, ask you to somehow sketch its inverse. And all you have to do is know that the inverse means swap the ordered pairs, swap the X's and the Y's. Okay, in a minute, I'll have you do the same thing on another problem. But on this original problem in black, I want to know, is it a function? What's its domain? What's its range? If I could spell, that'd be great. Okay, that's the original one I've done in black. And then I want you to do the same thing for the inverse. Is the inverse a function? Okay, what's its domain? What's its range? So let's pause while you think about that for a moment. So is the black graph, the original one, is it a function? Easiest
Yeah.
way? Yeah, it is. Good. Easiest way is to take your vertical line and it only hits one point at a time on the black graph. So yes, it's a function. Now, the domain means all of the X's. Now, be very careful. It's not just the end points of the X's. The black graph is the endpoints and all the little X's all in between. So the domain of the black graph is from -5 all the way up to 6. All possible X's, not just the endpoints, but all the little fractions and decimals in between. Okay, so that's how you have to write that infinite number of values between -5 and 6. All right, the range. The range is all possible Y values. The Y values go from -1 up, over, up to 7. So the range is from -1 to 7. Okay. Again, I'm literally telling you, this is a question on exam number 3. Guaranteed. All right, now we come around to the inverse, the red function. Okay, so we're going to ask the same questions. Is it a function? Okay. Now, it's kind of hard to tell this time because my graph, my drawing is sloppy, but okay. And then right here, a whole bunch of points are hit at the same time. When I take my vertical line and pass it through, I'm okay here, okay here, okay here. All of a sudden it dies. A whole bunch of points are hit all at one instant. So is it a function? No, it is not. Because of this segment right here. And also just because of these 2 points. Okay. This is, I think we had this as 2, 4. Well, here's 1x, 2, and it's matching with 2 different y values. That can't be a function. So 1x is going to 2 different y values, can't have it. Okay. Domain. Again, this is the domain of the red one. Okay. Where they go, the domain is everything from -1, everything to 7. So domain. -1 over to 7. Okay, range. Range is the y values. They go from -5 up to 6. Okay. Anybody see anything kind of weird about the domain and range of the function and the domain and range of the inverse?
They're just the same thing, but flip.
Okay, that's exactly right. Why are they flipped?
Because you switched the X and the Y.
Bingo. That's exactly right. So, cool little trick. If you know the domain of the function, you automatically know the range of its inverse. Okay. Or if you know the range of the function, you know the domain of its inverse. They're always switched. They're the same numbers, but switched because we swapped the X's and the Y's. Okay, I'm going to do some more of those tomorrow night. I'm not going to do any tonight. Let's take about a 5-minute break. Okay, that'll be like 8:05. We'll come back and we'll start all new stuff in chapter 10.2. Okay, 5-minute break. Okay, we're back. Some of us never left. So in chapter 10.2, everything, think about this. Everything that we talked about, functions, domain and range, inverses, composite functions, all of that was shoved into one section of chapter 10.1. Wow, that's a lot. Now we're moving on to section 10.2. We're going to study exponentials, things with exponents. Okay, we're going to have 3 topics tonight. We're going to talk about their graphs, exponential function or exponential graph, equations, and then we're going to do word problems using formulas that have exponents in it. Okay. And if we have time, I've got something else I want to do, but we'll worry about that. For the most part, these are, again, I see how they're related, but I also see how students don't see the relationship between these yet. So I can teach these as separate ideas. Let's go with the graphs first. Okay, let's go with the graphs first, exponential graph. And let's start with the easiest. Let's start with f of x equals y, which equals 2 to the x plus 1. Okay, it's a function. So we say f of x, but f of x is the same as y. Okay, so for the rest of this chapter or the rest of this section, I'm just going to write y equals. It still means f of x. It's still all the same. Notice something very, very important. This is 2 to the x. This is not x to the 2. Those are 2 totally different animals, completely different animals. Okay, and you'll get a totally different looking graph if you screw up the 2 to the x versus x to the 2. Be very, very careful. Now, if this were Math 116 or Math 121, I would assume that you've been exposed to this, and then I would start showing you some shortcuts. But right now, I'm also assuming that not too many people have seen this, so I'm going to go back to basics. If I want to graph this, okay, the safest way to do it right now is to build a table of values. Okay, and just start plugging in numbers. So easiest is if x is 0. So we have 2 to the 0 plus 1 is 1 plus 1 is 2. Remember, anything to the 0 power is 1. So I have 1 plus 1 is 2. Okay. What if x is 1? 2 to the 1 plus 1. That's 2 plus 1 is 3. What if x is 2? 2 to the 2 plus 1 is 5. That's good enough. You get the idea. But what if x is negative 1? What if x is negative 1? Then this is 2 to the negative 1 plus 1, which is 1/2 plus 1, right? Remember, negative powers, negative number or negative power means flip it over. So this is 1/2. What if x is negative 2? So this is 2 to the negative 2 power plus 1. Okay, this is 1/4 plus 1, which is 1 1/4. And I'm going to go one more, 2 to the negative 3. Just trust me, it's 1 1/8. Okay. As you guys know, I never make mistakes, so you know that I'm correct there when I say 2 to the negative 3 is 1 1/8. All right. Now, you can decide how many numbers you want to build in your table. If you've got a pretty good idea, you only do 1 or 2 positives and 1 or 2 negatives, great. I don't care. But I'm telling you that right now, the safest way is to build a table of values. However many points you need in order to determine the graph is strictly up to you. But let's plot this. When x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 5. Kind of like that, roughly. Okay. Now comes the fun stuff. When x is negative 1, y is 1.5. So sort of like there, somewhere between 1 and 2. When x is negative 2, y is 1 1/4. Well, here's negative 1, here's negative 2. 1 1/4. Okay, it's real hard to see on my graph. Negative 3, 1 1/8. Whoops, 1 1/8. Okay. Now, something really, really, really important is happening. Look what happens as x gets negative over here. The y values keep getting smaller, 1 1/2, 1 1/4, 1 1/8. The next one will be 1 1/16. Okay. So as the x's get negative, the y values are coming down, but they're not coming down to 0. They're approaching what number? 1 1/2, 1 1/4, 1 1/8, 1 1/16, 1 1/32. What are the y values coming close to?
2, 1.
To 1. That's so important, guys. This is approaching 1. So our graph, okay, first off, introduces the concept of something called an asymptote. This is called an asymptote, asymptote. Our graph has an asymptote. An asymptote is a boundary line that the graph cannot cross. It's coming down towards that asymptote, but never quite touches it. Okay. No matter how negative x is, okay, this number will always be a little bit bigger than 1. So when we graph this, okay, we must draw in the asymptote. Okay, we must draw the asymptote in. You have to show me you recognize the asymptote. Okay, you must give me the equation of the asymptote. This is a horizontal line, so it's y equals 1. That's the asymptote. Okay, there's my graph. When I connected the dots, there's my graph. As x comes more and more negative, the graph, if we had a graphing function, which I was going to show you tonight, I don't know if we will, we'll come down here and it'll always get closer and closer to 1, but never touch it, ever, ever. Okay, so that's what this asymptote is. That's a sketch of this graph. Now, one of the things I'm going to ask you always is this a function? And the answer is yes, because you can take the vertical line. What's its domain? Well, this is a little bit tricky because there's 2 ways to indicate the domain. You could say that x's go from -infinity to +infinity. Just think about this. The domain is the x's. They're going to go way out here to -infinity, or they're going to go out here to +infinity. Or the alternate way is a fancy R. Those are 2 ways to say everything. This says from -infinity to +infinity on the number line. That's what the fancy R says. They're the same thing. Okay, what's the range? Okay, the range is the y values. Notice they do not touch 1. They go from 1, almost 1. So we use a parenthesis, almost 1, and then the y values go up to +infinity. So there's, within reason, okay, a question on exam 3 and questions on mom. Okay, a question on exam 3 and questions on mom. So how do we do it? Built a table of values. You pick as many numbers as you want to help you get the shape of the graph. Okay, you must draw the asymptote as a dotted line. The asymptote, okay, there's a difference between humans and math. Math would say, oh, there's an asymptote there. Humans would go, where the hell is it? I don't see it. So we have to draw it in and give its equation. Notice something. Look at the equation. Okay, look at the asymptote. Look at its equation. The formula is trying to get me to tell me what the asymptote is. It's trying. It's right there. Okay. The only difference between this example and other ones on mom is they make the formula more complicated. Okay, like they do y equals 3 times 2 to the x plus 5 or something like that. And all that does is make your arithmetic more complicated. You still take numbers, you still plug them into your calculator or whatever. Okay, you can use your calculator. I didn't here because I wanted you to see what I was thinking. But you, even if they give you some really incredibly ugly formula, it's okay. Make a table of values, plug them in, plot them. Always look for the asymptote. It's going to be there. Its equation. And sometimes mom will ask, is it a function? What's its domain and range? Sometimes she won't. On the exam, I will ask, is it a function? What's its domain? What's its range? Okay, I want you then to do this problem. I'm going to have to erase this because I wrote too big. But I want you to graph y equals 3 to the x minus 2. Take a second to graph y equals 3 to the x minus 2. Okay, and then give me the domain range and is it a function? So let's build ourselves a big old XY table. Again, if x is 0, we have 3 to the 0 minus 2, which is 1 minus 2, which is negative 1. If x is 1, that's 3 to the 1 minus 2, which is 3 minus 2, which is 1. If x is 2, that's 3 to the 2 minus 2, which is 7. All right, that's enough. Okay, it's going, I got an idea for when x is a positive number. Now, what about when x is negative? When x is negative 1, this is 3 to the negative 1 minus 2. Be careful. This is 1/3 take away 2. This is negative 1 2/3. Or 0.666 or whatever your calculator says, but it's negative. Be very careful. Remember, subtraction is a killer. When x is negative 2, this is 3 to the negative 2 minus 2. This is 1/9 minus 2. So this is negative 1 8/9. If x is negative 3, I'm only going to do this last one. This is 3 to the negative 3 minus 2. This is 1/27 minus 2. Excuse me, my voice is going. So this is negative 1 26/27, whatever in the world that is. Okay. Let's see if we can see what's happening as x is getting more and more negative. As x is coming negative, my y values are negative, but they're always staying 1 and a little bit. 1 and a little bit. Negative 1, I'm sorry, and a little bit. What are they coming close to? What are these numbers? If we keep going down, what are the y values approaching? What are they coming close to?
-2.
Negative 2. Negative 2. Asymptote. Okay, they're approaching negative 2. By the way, the word approaching is calculus language. We use that quite a bit. In calculus, we always have situations where we can't quite get to the number, wherever we want to get to, but we approach it. We're coming closer to it. All right, so real quick. Okay, my asymptote is negative 2. Okay. Okay, this is y equals -2. There's my asymptote. When x is 0, y is -1. When x is 1, y is 1. When x is 2, y is 7. Yo. Okay, I'm not even going to bother with these things. It gets too messy. I know my graph looks like this and approaches the asymptote. Never crosses it, doesn't touch it, doesn't cross the asymptote. Okay, is it a function? Yes. Its domain is either -infinity, +infinity, or you can do the fancy R, because x's go to -infinity, and eventually, even though it's going up, the x's are going also to +infinity. So that's what the domain says. Range is from -2 up, but it can't touch -2, so we use a parenthesis, and it goes up forever to infinity. And that's a good enough graph for me. Like I said, the only difference between the problems I'm giving you here and some of the ones you're going to see on Mom is they give you uglier functions, harder to do your arithmetic with. Okay, but if you use the table of values and you go real slow, notice on both of these examples, why is my voice going? I don't know. I always stopped and looked at what were my y values doing? Were they approaching a number? Did they seem to be zeroing in or focusing in on a certain number? So I had to do some critical thinking. I had to think here, analyze. What was that critical number? That's probably my asymptote. Okay, want to leave that. That was functions and graphs, part of 10.2. You can do it, or come back tomorrow or next Tuesday and ask questions. I need to erase the board and move on to equations. Anything up here anybody wants to yell at me about? Okay. All right. I kind of misled you. These are called same base exponential equations. Okay, same base. And that's very important because it means these problems can be done without a calculator. Next week, we will discuss exponential equations and not the same base. Okay, and there's a whole different way those are solved. But if they're same base exponential equations, okay, I'll show you. Easiest example. Suppose you had 5 to the 3x minus 7 equals 5 to the x minus 4. These are called same base exponential equations. The base is 5. Okay. What? There's a little bit of trickery here. If the bases are the same and they are equal, doesn't that imply that the powers had to be the same. Okay, that's the whole trick here. If the bases are the same and they're equal, which is what this says, then it means the powers had to have been the same. There's no other logic to this. So basically we're saying the bases were unimportant to this problem because they were the same. Okay, so we could solve this, take away x from both sides, add 7. I think I get that. Is that right? Yeah, okay. And solve x is 3/2. It's an equation, so solution set 3/2. It's that easy, guys. Well, it's not that easy. Watch my next example. But that's the basic concept. If the bases are the same, okay, then the powers have to be the same. So you can drop the bases and just work only with the powers. Okay, that's the whole crux of this idea. Well, the question then becomes, well, okay, it was that easy. What's Foster going to do to really screw us up? Okay. What if I had 25 to the 3x minus 1 equals 125 to the, I don't know, let's say 7x plus 1. Okay. The bases are not the same. Okay, they're not the same. So your first inclination is to go, I can't do it. Because this rule of dropping the bases only works if they're the same. Okay, well, what do I do? Well, you use your knowledge and you go, yeah, but if I look inside of 25, I see a 5 squared. And if I look inside of 125, I see a 5 cubed. So this problem is 5 squared to the 3x minus 1 equals 5 to the third to the 7x plus 1. So the trick here is you have to be able to look inside the bases and ask, do the two bases, can they be reduced to something the same? 25 was 5 squared. 125 was 5 to the third. Okay. Well, now our rules of exponents kick in. What do you do with a power raised to a power? You multiply. So this becomes 5 to the 6x minus 2. A power raised to a power, you multiply the powers. This becomes 5 to the 21x plus 3. Again, in your notes, make sure you write power to a power, you multiply the powers. You keep the base, but multiply the powers. This goes back to chapters 4 and 5. I think it was chapter 5. Okay. And it was also the start of chapter 9. We kind of reviewed those rules too. All right. Well, now they have the same base. Okay. So now I can drop the base and have 6x minus 2 equals 21x plus 3. And then solve it really simple. What do I do? Take away 6x. Take away 6x. Take away 3. Divide by 15. Oh yeah, reduce. And solution set it. And I'm done. So the key is they have to have the same base. As the instructor, who's out to get you, I will hide the base from you, but it will be there. You just have to know your multiplication skills. Okay, want to do one last example, then get to word problems here. And again, we'll worry about some of these tomorrow night. What if I had can I erase this equation here? I'm going to need more room for this next example. Anybody have a question about this first example I used? Okay. What if I had 2 to the 3x plus 1 times 4 to the 5x minus 6 equals 16 to the negative 4x minus 7. Now this has a major trick in it. So I need to make sure you guys kind of see it. And again, we'll talk more about these tomorrow night. We'll give some more review and stuff. Again, the game is we've got to look inside the numbers and see if we can break them down to having the same base. Okay, so I can't break 2 down anymore. So this 2 is going to say 2 to the 3x plus 1. But I can break down 4. 4 is 2 squared to the 5x minus 6. And 16 is 2 to the 4th to the negative 4x minus 7. Again, your knowledge, your multiplication skills, all the practice we've been doing with powers, okay, and factoring and all that kind of stuff, that's all coming to bear right now. But you could certainly go off to your scratch paper and play around. How can I write 4 as a power? 2 squared. How can I write 16 as a power? Again, if you weren't sure, take 16, break it into 4 times 4, which we break into 2 times 2 times 2 times 2. That's how I got 2 to the 4th. Okay. But if you could do it in your head, great. If you need to go to scratch paper, great. Doesn't matter. All right. This becomes, okay, this stays 2 to the 3x plus 1 times, this is a power raised to a power. So this is 2 to the 10x minus 12. This is a power to a power, so it equals 2 to the negative 16x minus 28. Okay, watch carefully. Okay, we can't drop the bases now. Okay, I didn't make a big deal about this before. You got to get this in your notes. There has to be one base on this side and one base on this side. It's got to be 1, 5 to a power equals 1, 5 to a power. Single bases. Okay. This has double bases. You can't drop them yet, but you can use your knowledge of exponents. What do you do if you had 2 to the 3 multiplied by 2 to the 7? Okay. Well, the rule was when we're multiplying with the same base, the rule was keep the base, add the powers. So this is going back to our basic rules of exponents. When you had a power raised to a power, you multiplied them. Keep the base, multiply them. But when you had a power times a power, You keep the base, you added the powers. Okay, well, what's that got to do with anything? This could be combined into 2 to the 13x, add the powers, minus 11, equals 2 to the negative 16x minus 28. So there's all kinds of tricks in this problem. Now you can drop the powers. Now you can say 13x minus 11 equals, what do I have here? Negative 16x minus 28. And then go from there. That's 29x equals, add 11, negative 17. I think that's right. Add 16, and you get 29. Okay, add 11, so 11, yeah, 17. So x is negative 17 over 29. Negative 17, dummy. And of course, I wrote it right in the glare. So this problem here, okay, another example of you needed to look inside the bases and ask, what number do they all have in common? What base can I break them all down to? And it was always base 2, base 2, base 2. So I start with, okay, 2 to the second to the 5x minus 6. I remember my rule. When you have a power raised to a power, you keep the base, you multiply the powers. Okay, but later I knew that I had to combine these two. Okay, so that a different rule, you keep the base, you add the powers. And now that they have one base 2 on the left side, one base 2 on the right side, now I can drop the powers and finish solving the problem. Okay, I want to do one word problem and then I'm done. And then we'll pick this up tomorrow night. I want to do one word problem. And you will need your calculator for this. Okay. I will always give you the formula to use. Now, whether mom will or not, I don't know, but you have your notes with you. But when it comes to a test, I will always give you the formula that you're going to use for each one of these problems. Your job is to use the formula correctly. Now, there's a concept called compound interest. Okay. And its formula looks like this: A of t equals P times 1 plus R over N raised to the N T. Now, let's change this a little bit because the problems that mom uses, A of t, she calls this FV, which is future value. Okay. And that's what A of t would stand for. What's the amount or the value in a certain time in the future? So in math talk, we say A of t, the amount or the value in the future after a certain amount of time. But the problems that I selected from mom on this, and I went through and modified most of them, they use sometimes the phrase FV, future value. Okay, I don't like it because it's not math stuff, but it doesn't matter. Okay, so FV equals P times 1 plus R over N raised to the N times T. Now we need to talk. What is P? P is the initial amount, also known as the principal. How much money are you putting in? P is the initial amount of money that you started with. Okay. R, little r, is the interest rate very important as a decimal. So if we tell you the interest rate is 2.5%, you have to use 0.025. You have to convert it. The word problems we'll talk about, the interest rate is 2.5%, or their interest rate is 1.71%. Well, you have to remember how to convert it to 0.0171 as a decimal. So R is the interest rate, but written as a decimal. Okay. T, where's my, okay. T is time. That makes sense. Okay. N is the tricky thing here. In the bad old days, and by that I mean before they invented fancy calculators or calculators, anything, N was always once. They always did your calculations one time a year. But compound interest is what all the banks use now, and they can do the calculation as many times a year as they want. Okay, so if they said weekly, N is 52 because there's 52 weeks in a year. If they said we're going to compound this weekly, okay, we're going to do the calculation weekly, then you put a 52 here for N. If they say monthly, then N is 12. Okay, we're going to calculate this every month. So N is 12. You put 12 here, 12 here. Okay, if they said semi-annually, N is 2. Semi means twice a year. Doesn't Macy's or Nordstrom's have a semi-annual sale? So I'm saying N is 2. So whatever. I mean, that's what you do here. And it's just a matter of plugging numbers in and using your calculator correctly. That's all it is. That's all we're going to do now. Later, we'll make it more complicated. But right now, we want to introduce you to this formula. So let's say you have, for example, let's say you have $1,000 that you want to put in the bank. They promise you that you're going to get 2.1% interest. And they're going to compound it monthly. Okay, this is what they promise. Okay, but you have to leave the money in the bank for 3 years. Now, I'm just making this up. My wife and I just refinanced our house. We got a pretty good rate actually, but God, it was terrible trying to keep track of all the money going in and out and all the restrictions. It's terrible. Okay, so we got $1,000. Okay, we get 2.1% interest. We're going to compound it monthly, meaning our calculation is going to be done every month. Okay, and we're going to do it for 3 years. What is the future value? So your work would look something like that. Future value equals 1,000 times 1 plus 0.021 over 12, close parentheses. Okay, the 0.021 was the interest rate as a decimal. Okay, the 12 was because it said monthly. Okay, and it will be raised to the 12 times 3. The formula up here was n times time. Well, n was 12 in this problem, so we use it twice. We use the n 2 different times here and here, and time was 3 years. So the rest of this, all of this now is done on your calculator. That's it. The rest of it. Okay. So what do I have? Clear. I, on my calculator, start with this 0.021 divided by 12, add 1. Now, what I have right now is 1,000 times, my calculator says 1.00175, and this is 36. Remember, PEMDAS says start on the inside, but on the inside we have division. So I had to divide these first and then add it to 1. So this is my reduced problem. 12 times 3 happens to be 36. Now, what do I do with this? First, you have to do exponents. So first you have to raise it to the 36th power. Okay. Where is it? Oh, on the TI, you have an x to the box power. Okay. So you can push, well, there's 2 ways of doing this. How do I want to do it? How do I want to show you this? Okay. If you push X to the box, it'll say answer box on your calculator. If you push that button on the TI, other calculators have something very similar to this. I'll have to help you tomorrow. But in the box, I put a 36. So it's got that last answer, and I put a 36 there. Okay. And then that gives me 1.06. So what I have now is 1,000 times 1.064962. So I just take that times 1,000. And I get 1064.9682. And since this is money, you have to pay attention to what it says, but it would be 97 because money is only in dollars and cents. So your future value, if the bank or credit union offered you this deal, you give them $1,000, they keep it in the bank for 3 years at these rates. At the end of 3 years, you have $1,064.97. Okay. We'll do more of these tomorrow and much more. Remember, somewhere a little bit after 8 o'clock, we're going to have a quiz tomorrow. See you then. Bye-bye.